Good morning, one and all. Welcome to the lecture on image compression. This is a topic that comes under the course Digital Image Processing for S6 EC students. I am Sherry Ann Sacharias, Assistant Professor in the Department of Electronics and Communication at Rajagiri School of Engineering and Technology. The contents of the presentation are as follows. We'll start with an introduction to what is image compression. Then we'll discuss on the types of redundancies present in images. We will move on to discuss the classification of compression schemes, and then we will discuss on two types of lossless compression techniques, namely the Huffman coding and arithmetic coding. The rapid growth of digital image applications has increased the need for effective image compression. What is image compression? Image compression deals with techniques used to reduce the amount of data needed to represent a digital image with acceptable quality. The need for image compression. Web page images, high-resolution digital camera photos require a large amount of storage space. Compression is used to reduce the size of an image, thereby increasing the number of photos that can be stored on a given flash memory card. Large amounts of data transmitted over the internet comprises of images. Reducing the bandwidth needs of a device results in a significant cost reduction. Compression also reduces the transmission time, which is significant in applications such as teleconferencing, remote sensing, medical imaging, and so on. Image compression is possible because digital images are highly coherent in nature. Encoding regions of constant intensity results in duplication or repetition, which is known as data redundancy. Image compression is achieved by removing this redundancy. Redundancy can be classified into two kinds: statistical redundancy and psychovisual redundancy. Statistical redundancy is based on the statistical analysis of digital images, whereas psychovisual redundancy is associated with the characteristics of the human visual system. Statistical redundancy can be further divided into interpixel redundancy and coding redundancy. Interpixel redundancy is due to the similarity of neighboring pixels in an image. Coding redundancy is based on the characteristics of the code used to encode each pixel. It can be overcome using efficient coding schemes. Coding redundancy. A digital image is represented as a two-dimensional array of intensity values. Each intensity value is represented in the form of a code. The number of bits used to represent an intensity value may be more than what is actually required. Here is an example of an image of size 256 cross 256 in which each pixel can take one of 4 intensity levels. Each intensity level is encoded using 8 bits, which leads to coding redundancy. For any compression scheme, the compression ratio is defined as C is equal to B by B dash, where B represents the number of bits used to represent the original image and B dash represents the number of bits used to represent the compressed image. Data redundancy is related to the compression ratio as R is equal to 1 minus 1 by C. For example, a compression ratio of 10 leads to a redundancy of 0.9, which shows that 90% of the data in the original image is redundant. Consider a digital image which has L representation levels. For any coding scheme, the average number of bits used to represent each pixel is given by L average is equal to summation k is equal to 0 to L minus 1 L of Rk into P of Rk, where L of Rk represents the number of bits used to represent the kth intensity level and P of Rk represents the probability of finding the kth intensity level in an image. For an image of size m cross n, the number of bits used to represent the entire image is the size of the image mn times the average length. Here is an example of a digital image of size 256 cross 256 which is encoded using two coding schemes, namely code 1 and code 2. The first column of the table shows that each pixel of the digital image can take one of four intensity values, namely 87, 128, 186, and 255. The second column shows the probability of finding each intensity level in the given image. Code 1 is an example of a fixed coding scheme in which each intensity level is encoded using a fixed number of bits. Here in this case it is 8. So using code 1, the average number of bits used to represent each pixel is 8 and the total number of bits used to represent the entire image is given by the size of the image, which is 256 cross 256 times 8. Code 2 is an example of a variable coding scheme in which the intensities with higher probability are assigned a lower number of bits, whereas the intensities with lower probability are assigned a higher number of bits. So the average number of bits used to represent each pixel is given by summation over k, L of Rk into P of Rk, where L of Rk is the number of bits used to represent each intensity level and P of Rk is the probability of finding each intensity level. So we calculate L average using code 2 is 1.81 bits and the total number of bits used to represent the entire image is given by 256 times 256, which is the size of the image times L average, which is 1.81. So you can see that there is a significant reduction in the number of bits used to represent the image using code 2 as compared to code 1. On comparing the two coding schemes, we find that the compression ratio achieved by code 2 is much better. So the compression ratio is given by C is equal to B by B dash, where B represents the number of bits used to represent the image using code 1 and B dash represents the number of bits used to represent the image using code 2. So we get a compression ratio of 4.42. With this, we find the data redundancy where R is equal to 1 minus 1 by C. So we get a redundancy of 0.774, which shows that 77.4% of the data which was encoded using code 1 is said to be redundant. Next type of redundancy is spatial and temporal redundancy. Spatial redundancy is due to the relation between neighboring pixels in an image. So while encoding regions of same intensity, information may be duplicated. Here is an example of a digital image of size 256 cross 256. If you look along each row, pixels have same intensity, which leads to spatial redundancy. On the other hand, temporal redundancy refers to the similarity between pixels in the successive frames when we consider a video sequence. Psychovisual redundancy. Most two-dimensional intensity arrays contain information that is often ignored by the human visual system. In the human visual system, all intensities are not perceived equally. Some information may be more important than others. So even if less data is used to represent the less important visual information, perception is not affected. Here is an example of a 256 cross 256 image in which each pixel is encoded using 8 bits. This leads to a redundancy as every pixel in this image has the same intensity level. So the image can be represented by its average intensity alone, which is a single 8-bit value. Image compression schemes can be classified into mainly two categories: lossless compression and lossy compression. In lossless compression, compression is achieved by removing only the redundancies present in an image. This means that the reconstructed image will be an exact replica of the original image. However, the compression rate achieved using this method is moderate. It is used in applications such as medical imaging and remote sensing. Lossy compression, on the other hand, compression is achieved by removing redundancies as well as information present in the image. This means that the reconstructed image will have certain degradations with respect to the original image. However, a much higher compression rate can be achieved. This is used in applications such as multimedia, where certain amount of degradations are acceptable. Now, the performance of any coding scheme is measured in terms of its efficiency, which is in turn measured in terms of the entropy of the source code. So what do you mean by entropy? Given a source of statistically independent random events from a discrete set of events A1, A2, etc., Ak, with probabilities P of A1, P of A2, etc., P of Ak, the entropy or average information per source output is defined as H is equal to summation over I P of Ai into log 1 by P of Ai, where P of Ai is the probability of each event. This is the block diagram of an image compression scheme. The input image is given to a source coder. The source coder converts the source image into a sequence of bits, and the purpose of source coding is to remove any redundancies and reduce the average number of bits used to represent the image. This is then given to a channel coder. The channel coder introduces a certain amount of controlled redundancy in order to protect the data from further transmission errors as it propagates through the channel. At the receiver side, the inverse operation of channel decoding and source decoding is done in order to get back the decoded image. In this lecture, we will be focusing on source coding techniques. Now we will discuss on two types of lossless compression techniques, namely the Huffman coding and arithmetic coding. In Huffman coding, a binary code is assigned for each intensity level, and it uses shorter codes for intensities with higher probability. Arithmetic coding, on the other hand, assigns a single arithmetic code to a sequence of source symbols. Huffman coding is an example of a lossless compression technique in which a binary code is being assigned to each source symbol. The procedure of Huffman coding is as follows. The first step is to arrange the source symbols in the decreasing order of probabilities. Once the source symbols are arranged, the two symbols having least probability are assigned a 0 and a 1. Then the two symbols having least probability are combined to form a new symbol with a probability equal to the sum of the two original probabilities. This is then placed in the second column, which is arranged in the decreasing order of probabilities. This procedure is repeated until we are finally left with two symbols to which we assign a 0 and a 1. The code for each source symbol is then found out by working backwards and tracing the sequence of zeros and ones assigned to each symbol. Now, we will look into an example and see how Huffman encoding can be done. So, given a source with symbols S1, S2, S3, S4 and S5 with probabilities 0.4, 0.2, 0.2, 0.1 and 0.1, our aim is to construct a binary code using Huffman encoding and analyze its performance by finding the entropy of the source, the average code length, code efficiency, and variance. So the first step in Huffman encoding is to arrange the source symbols in the decreasing order of probability. Once the source symbols are arranged in the decreasing order of probability, the two symbols having least probability are assigned a 0 and a 1, and these are combined to form a new symbol with a probability equal to the sum of the original probabilities. This step is repeated till we are finally left with two symbols to which a 0 and a 1 are assigned. The code of each source symbol is then found out by tracing the sequence of ones and zeros back to the source symbol. So the table over here shows the code which is formed corresponding to each source symbol. We will look into this a little more in detail. So the source symbols S1, S2, S3, S4 and S5 are arranged in the decreasing order of probability. Once the source symbols are arranged, the two symbols having least probability are assigned a 0 and a 1. These two symbols are combined to form a new symbol having a probability 0.1 plus 0.1 is equal to 0.2. The symbols are again arranged in the decreasing order of probability, and the symbols with least probability are assigned a 0 and a 1. These two symbols having least probability are then combined to form a new symbol having a probability 0.2 plus 0.2 is equal to 0.4. In the third column, again, the symbols are arranged in the decreasing order of probability, and the symbols having least probability are combined to form a new symbol having a probability 0.4 plus 0.2 is equal to 0.6. We are finally reaching the last column in which we are left with two symbols to which we assign a 0 and a 1. In the final step, we will trace back the sequence of ones and zeros to each source symbol. So if you look at the symbol S1, we can find that the code corresponding to S1 is 1. Corresponding to S2, the code that is obtained is 0, 1. The code corresponding to the source symbol S3 is 0, 0, 0. The code corresponding to the symbol S4 is 0, 0, 1, 0. And the code corresponding to the symbol S5 is 0, 1, 1, 1. The average code length is calculated using the formula L average is equal to summation over I L of Si into P of Si, where L of Si represents the number of bits used to represent each symbol and P of Si represents the probability of each symbol. So we can calculate the average code length L average and we find its value is equal to 2.2 bits per symbol. Similarly, the entropy of the source is calculated as h of s is equal to summation over I p of si into log to the base 2 1 by p of si, where p of si represents the probability of each source symbol. So the entropy of the source h of s is calculated as 2.12 bits per symbol. The efficiency of any encoding scheme is calculated as the ratio of the entropy of the source to the average number of bits used to represent each symbol. So here eta is defined as HFS divided by L average, which is calculated as 0.963. So the efficiency of this Huffman encoding is 96.3%. Similarly, the variance of the code is calculated using the formula sigma square is equal to summation over I P of Si into L of Si minus L average the whole square, where P of Si is the probability of each symbol, L of Si is the number of bits used to represent each symbol, and L average refers to the average number of bits used to represent a symbol. So for best coding schemes, the efficiency should be as high as possible and the variance should be as low as possible. Arithmetic coding is another example of a lossless compression technique. In arithmetic coding, a sequence of source symbols is being assigned a single arithmetic code. The code word defines an interval of real numbers between 0 and 1. So as the number of symbols in the message increases, the interval used to represent it becomes smaller and the number of bits used to represent the interval becomes larger. Arithmetic coding performs well for sequences with low entropy as compared to Huffman coding. The procedure for arithmetic coding is as shown here. The first step, we consider an interval from 0 to 1. This interval is then divided into the number of symbols according to the probability of occurrence of each symbol. The first symbol to be encoded is then expanded along with its range. This range is further subdivided into the number of symbols based on their probabilities. This procedure is then repeated until the last character is encoded. Now we will look into an example and see how arithmetic coding is performed. Given a source which emits 4 symbols A, B, C and D with probabilities 0.4, 0.2, 0.1 and 0.3, our aim is to construct arithmetic coding to encode and decode the word dad. So the word dad has 3 symbols D, A, D. So in the first step, we are going to consider an interval 0 to 1. And this interval 0 to 1 is going to be divided into 4 based on the symbol probabilities. So the subrange of A is 0 to 0.4 as the probability of A is 0.4. The probability of B is 0.2, which means the subrange of B is 0.4 to 0.4 plus 0.2, which is 0.6. The probability of C is 0.1, which shows that the subrange of C is 0.6 to 0.6 plus 0.1, which is 0.7. And the probability of D is 0.3, which shows that the subrange of D is 0.7 to 1. In the second step, we will consider the first symbol to be transmitted, which is D. The subrange corresponding to D is 0.7 to 1. So the new interval that we should consider is 0.7 to 1. So this new interval 0.7 to 1 has to be further subdivided into 4 based on the symbol probabilities. So the new range for each symbol is defined as lower limit to an upper limit, where the upper limit is defined as lower limit plus D into probability of the symbol, where D is defined as the range of the interval, which is the upper bound minus the lower bound. The range D in the interval 0.7 to 1 is the upper bound minus the lower bound, which is 1 minus 0.7, that is equal to 0.3. So in this new interval 0.7 to 1, we'll calculate the subrange for the symbol A as the lower limit, which is 0.7, to the upper limit. The upper limit is calculated as lower limit plus D into the probability of the symbol. So D is 0.3 and the probability of A is 0.4. So we get the subrange of A as 0.7 to 0.82. Similarly, the new range for the symbol D is computed as the lower limit, which is 0.82, to the upper limit. The upper limit is calculated as the lower limit 0.82 plus D, which is 0.3, into the probability of symbol B, which is 0.2. So we get the subrange of B is 0.82 to 0.88. The subrange of B can be seen as 0.82 to 0.88. Similarly, the subrange of symbol C is computed as the lower limit, which is 0.88, to the upper limit. The upper limit is calculated as the lower limit plus D, which is 0.3, into the probability of symbol C, which is 0.1. So we get the subrange of C as 0.88 to 0.91. Thus, the interval 0.7 to 1 has been divided into 4 based on the symbol probabilities. The range D in the interval 0.7 to 0.82 is calculated as the upper bound 0.82 minus 0.7, which is equal to 0.12. So this new interval 0.7 to 0.82 has to be divided into 4 based on the symbol probabilities. So the subrange for the symbol A in the interval 0.7 to 0.82 is computed as the lower limit, which is 0.7, to the upper limit. The upper limit is calculated as the lower limit 0.7 plus D, which is 0.2, into the probability of symbol A, which is 0.4. So we get the subrange of A as 0.7 to 0.748. Similarly, the new subrange for the symbol B is computed as the lower limit 0.748 to the upper limit. The upper limit is calculated as the lower limit 0.748 plus D, which is the range 0.12, into the probability of symbol B, which is 0.2. So we get the subrange of B as from 0.748 to 0.772. In a similar way, the subrange of the symbol C is computed as the lower limit 0.772 to the upper limit. The upper limit is calculated as the lower limit 0.772 plus D, which is the range 0.12, into the probability of C, which is 0.1. Thus, we get the subrange of C as from 0.772 to 0.784. Thus, the interval 0.7 to 0.82 has been divided into 4 based on the symbol probabilities. Now we will consider the last symbol to be transmitted, which is D. So the subrange corresponding to D is 0.784 to 0.82. So any value within this interval can be transmitted in order to denote the message tag. After considering all the symbols to be encoded, that is D, A, and D, the final step is the computation of the tag value. The tag value is defined as the average of the lower and upper limits of the final interval. So here in this case, our final interval is 0.784 to 0.82. So the tag value is computed as the average of the upper and lower limits, which is 0.784 plus 0.82 divided by 2. So we get a value of 0.802. Hence, the tag value of 0.802 is the arithmetic code corresponding to the message DAT. Now we will consider the decoding procedure corresponding to the arithmetic code. So at the receiver, the tag value and symbol probabilities will be known. So our aim is to decode the data from the tag value. So for the above problem, let us try to decode the transmitted data given that we know the tag value 0.802 and the symbol probabilities A, B, C and D. In the first step, we will consider the initial interval 0 to 1 and the tag value 0.802 is being compared with the symbol subrange. So on comparing the tag value with the symbol subrange, we find that the tag value 0.802 lies in the subinterval 0.7 and 1, which corresponds to the subrange of the symbol D. This shows that D is the first symbol that was transmitted. In the second step, since we know that the first decoded symbol is a D, we will consider the new interval corresponding to the subrange of D, which is 0.7 to 1. In the third step, a new tag value is computed as T star is equal to the initial tag minus the lower limit divided by the range. So here in this case, T star is calculated as the initial tag value 0.802 minus the lower limit. So the interval that we are considering is 0.7 to 1. So the lower limit is 0.7 divided by the range. The range of the interval is 1 minus 0.7, which is 0.3. So we get a new tag value of 0.34. This tag value lies in the range of 0 to 0.4, which corresponds to the symbol subrange of A, which means that the next decoded symbol is A. So once you know that the next decoded symbol is A, we will consider the subrange of A as the next interval. The subrange of A is 0 to 0.4. So in this interval, we will compute the next tag value. So in the next step, the new tag value for the interval 0 to 0.4 is calculated as T star is equal to the previous tag, which is 0.34 minus the lower limit, which is 0, divided by the range. The range of the interval is 0.4 minus 0, which is 0.4. So we will get a new tag value of 0.85. This tag value lies in the interval 0.7 to 1, which corresponds to the subrange of the symbol D. This shows that the third symbol that was transmitted is D. So from the above steps, it is clear that the decoded word is dad. But the drawback of this scheme is that you require an end of message indicator to separate one message from another. Another drawback is the lack of a finite precision arithmetic. With this, we conclude this lecture series on image compression. So as a summary, we discussed what image compression is. Image compression deals with methods used to reduce the amount of data needed to represent images, we discussed on the need for compression and the different types of redundancies found in images. We also discussed on two error-free compression techniques such as Huffman coding and arithmetic coding. Thank you.